Landau theory is sort of the general way of looking at the mean field theory approach to second-order phase transition. The central idea is that we can think of the Helmholtz free energy as a non-singular function, which therefore we can expand in a power series in both temperature and an order parameter that characterizes whether we're in the broken symmetry low temperature phase or the manifest symmetry high temperature phase. So if I denote that order parameter, which you can think of as being like the magnetization in our spin system example, and we consider the temperature to be close to the critical temperature, so in particular temperature minus critical temperature small compared to 1 when we divide by the critical temperature, then the free energy as a function of order parameter and temperature has a constant term independent of the order parameter, which depends on the temperature, but imagine evaluating it at Tc or a value close to Tc. Then the important thing is that I'm assuming, by the way, that there's a order parameter goes to minus order parameter symmetry, like in the magnetic model. So there are no odd terms. The next term in the power series expansion in the order parameter is quadratic, and that quadratic term has a coefficient which changes sign at the critical temperature. I'm considering alpha to be positive, so that means that the quadratic term has a positive coefficient for temperature above critical temperature and negative for T less than Tc. And then there are higher order terms as well of all even powers, so the next most important term is psi to the fourth. So when the temperature is above the critical temperature, the free energy as a function of order parameter is quadratic in leading order. And right at the critical temperature, so this is for tau greater than tau c, right at the critical temperature, the free energy as a function of order parameter has no quadratic term, only a quartic one, so it gets very flat. And then as the temperature dips below the critical temperature, the quadratic term has a negative coefficient, so it turns down, but then the quartic term wins in the end and it turns over. And so the minimum of the free energy occurs actually at two non-zero values. And so in the low temperature phase, the order parameter has a non-zero value. So you can think of that as like the spontaneous magnetization in the magnetic model. So in particular, if you can ask, how does this value of the order parameter turn on when the temperature is just below the critical temperature, which we can find just by minimizing this function when tau is close to tau c and a little bit less than tau c. And so the minimum occurs when the square of the order parameter is linear in the deviation from the critical temperature. So Landau theory makes the prediction that the order parameter will behave like some constant with either a plus or minus sign times minus epsilon, where epsilon is this dimensionless deviation from critical temperature, to a power, which in general is called beta, and according to Landau, beta should be equal to 1/2. We can also consider the response when we introduce some external field that couples to the order parameter. So consider modifying the Helmholtz free energy by introducing some terms that break the symmetry due to some external field, like the magnetic field in the case of our ferromagnetic model. So the leading behavior will then be linear in the order parameter with some coefficient. So you can think of this as being like the applied field in the case of the magnetic model. That breaks the psi goes to minus psi symmetry so that when we're in the broken symmetry phase, when psi 0 is non-zero, one or the other of these two minima will be favored depending on the sign of lambda, whether it's positive or negative. When we fix the order parameter by minimizing this deformed, perturbed Helmholtz free energy, then the external field is derivative of Helmholtz free energy with respect to order parameter with temperature fixed. And then we can consider the susceptibility, which tells us when the in particular we're interested in the case where the temperature is close to the critical temperature and we turn on an external field, how does the system respond? The susceptibility then is the derivative of the order parameter with respect to the applied field with temperature fixed. So if you consider the inverse susceptibility, that's the derivative of lambda with respect to order parameter, the second derivative of the Helmholtz free energy with respect to order parameter with temperature fixed. And so if we use our expression for f, now take another derivative, we can write chi inverse, the second derivative, as a constant term which goes to 0 when tau is tau c, and then the next most important term for psi small is obtained by differentiating twice the quartic term, so that's a quadratic term, plus higher order. When we consider approaching the critical point from the high temperature phase, then in the most probable configuration psi is 0, and so the inverse susceptibility is going to 0 at the critical temperature, like alpha tau minus tau c. But if we're in the low temperature phase, we can replace this by psi 0 squared. So that's 0 for tau greater than tau c, but it's, wrote it down somewhere here. It's alpha over G4 tau c minus tau. When tau is less than tau c. So when we multiply by 3G4, this term, when tau is less than tau c, looks like this term, except with the opposite sign and with the coefficient 3. So what Landau theory tells us about the inverse susceptibility when we're close to the critical point is that it vanishes like linearly in the deviation from the critical temperature when we're in the high temperature phase. But 2 alpha tau c minus tau when we approach the critical temperature from below. Either way, the susceptibility itself is diverging at the critical point. Its inverse is going to 0. So Landau theory says that the susceptibility, as we approach the critical temperature, goes like epsilon or minus epsilon, depending on whether we're coming at it from positive or negative epsilon. So I'll say absolute value of epsilon to a negative power, call it minus gamma, and Landau says gamma is equal to 1. the inverse susceptibility goes to 0 linearly with tau minus tau c. It's still here. Okay. I hadn't discovered it until I bumped into it.
Every time you walk by, you should remove the block.
Yeah. By the end of the class, knowing my propensity for pacing, I'll probably go by it about 20 times. Okay. And there was also a prediction about the heat capacity, but I guess I'll skip over that. Of course, it also tells us something about what happens when we're on the critical isotherm right at the critical temperature. That means that the free energy is constant plus a quartic term, according to Landau theory. So when tau is equal to tau c, the equation which relates the applied field and the order parameter on that critical isotherm is that lambda, derivative of free energy with respect to psi, is goes like psi cubed plus higher order. So when we consider the response when the order parameter is small, it's psi cubed. So there's a prediction for the behavior of the equation of state when we're at the critical temperature. The applied field goes like order parameter cubed. So in general, the exponent that relates the two is called delta, and so Landau theory makes a prediction for delta, which is 3. And actually there's a more general statement about the equation of state when tau deviates away from the critical temperature, which is another one of the homework problems. Okay, so the neat thing about these predictions is that they're universal. They follow for any system as long as our basic assumption is satisfied, which is an extremely mild assumption. It's just that the Helmholtz free energy can be viewed as a non-singular function, which we can expand in a power series. Okay? And so they apply in particular to both our van der Waals model of the liquid-gas phase transition and our mean field model of the ferromagnetic phase transition, because both have that property, that they can be viewed as models in which the Helmholtz free energy is non-singular. Okay, so it's great to have universal predictions, but they're also wrong predictions. For these critical exponents, which tell us in particular how things behave when the temperature is close to the critical temperature, they're universal, but also wrong. Now, the actual situation is that there's a broad class of second-order phase transitions which have the same exponents. Exponents really are universal, but beta, instead of being 1/2 in practice, is something like 1/3, about 0.32, and gamma something like 1.3. So universality is a great idea, but there's something wrong with our predictions. But what's nice about the point of view we're currently taking is the predictions followed from such mild assumptions, which we've now learned must be wrong, that we can't think of the Helmholtz free energy close to the critical temperature as being a non-singular function. It actually has singular behavior. And in order to make correct predictions, we have to understand that singular behavior better. So what is it that goes wrong? Why is Landau theory wrong? Well, it has to do with the fact that our analysis has been aimed at trying to understand the most probable behavior, the value of the order parameter in equilibrium. But what we've ignored are the fluctuations around equilibrium. Usually, as in past discussions, the fluctuations are a small effect. So just looking at average values is fine for getting predictions that agree with the experiment. But close to a second order phase transition, fluctuations are very important. So what we conclude from this failure is that f is singular at critical point and the qualitative reason why because fluctuations of order parameter the order parameter psi about its mean value are large for epsilon small, that is for temperature close to critical temperature. So when we're approaching the critical temperature, like I said, the free energy function gets extremely flat. And you can think of this function as governing fluctuations. If in some region the order parameter departs from its mean value, it's not the most probable configuration. So now, usually we don't talk about dynamics when we think about equilibrium properties. But if we do think about dynamics, the free energy functional, if the fluctuation tries to climb up the potential, it's going to make it want to come back down, right? But it's going to come back down really slowly when the curvature of the free energy as a function of the order parameter is very small. The quadratic term, which is going away at the critical point, is responsible for the restoring force that makes a fluctuation relax back to order parameter equals 0. So because it's flat at temperature close to critical temperature, fluctuations in psi take a long time to relax. That's called critical slowing down. Usually the system is fluctuating around its most probable configuration, but those fluctuations have a short time scale. So you don't have to wait very long for the fluctuation to relax away. But when you're close to the critical point, that's not true anymore, and a fluctuation can take a long time to decay. So in fact, the fluctuations can grow very large in spatial extent as well as temporal extent. If you suppose you have a gas like water vapor above the critical temperature, and then you let it cool, and you pass through the critical temperature, what happens? Do you see anything strange happen while tau passes through tau c? Actually, what happens is it gets all cloudy. It's transparent when the temperature is a little bit above the critical temperature. It's transparent when the temperature is a little bit below. But right near the critical temperature, it gets all cloudy. Why does that happen? Well, it happens because there are big fluctuations in density. There are regions that are underdense and overdense. So which have a fairly big spatial extent. And the same kind of thing happens in a magnet, where you get big droplets where lots of spins are pointing in the same direction, and other big droplets where they're pointing in the opposite direction. So for temperature close to critical temperature, there are large regions where the deviation of the density from its mean value is negative or positive. And those regions get to be hundreds of nanometers in size, comparable to the size of the wavelength of visible light, so light gets scattered. So visible light in particular, the kind we see, gets scattered. And that's why it gets cloudy. That's called critical opalescence. Opalescence being a fancy word for you can't see through it. Okay? So what's happening when the temperature is close to the critical temperature is there are all these big fluctuations on big scales, and they take a long time to relax. So for temperature comparable to critical temperature, many length scales are important. We have, in other words, to figure out how to calculate the properties of a system in which there's dynamics occurring at all different scales of length. And that makes it hard to compute things. And this was a big problem for decades, but it finally got cracked in the early 70s. In particular, due to work by Kadanoff and Wilson, who used an idea which has a scary, fancy name, but it's not really, it's Kadanoff actually, with a D. Has a scary name, but it's not really such a scary concept. We call it the renormalization group. And their idea for tackling a problem which has fluctuations on all these different length scales is to do a kind of coarse graining of the system. So we have, let's say it's a spin system, like a magnet, like our model of a ferromagnet. So the spins in the spin system interact with their neighbors. So here's the spin system. There are a bunch of spins, may be arranged on a regular lattice, and each one interacts with its neighbors. Namely, there are interactions that make the spins want to line up in the same direction, which is going to give rise to ferromagnetism when the temperature is low enough. And as we start to cool the system down, starting at a high temperature, the spins get more and more correlated. Their tendency to line up with one another is becoming more and more important as the temperature gets lower. So as the temperature approaches the critical temperature, we start to get droplets of spins which all want to line up the same way. That's supposed to be a droplet of spin. And then there are other droplets where many spins are lined up the same way. we get large droplets of correlated spins. So now what do we do? Well, what Kadanoff and Wilson say is we should sort of coarse grain the system. We should look at it with a coarser spatial resolution. In other words, we should think of each one of these big droplets, which actually contains many microscopic spins, as like one big spin. And that's essentially what the renormalization group is. It's to replace many spins with sort of an averaged spin. That's what I mean by coarse graining. Now we're talking about going beyond Landau theory. So we take this droplet in which the spins are lined up in a common direction because the spins have lots of correlations, and we think of that as just one big or average spin. So now we can describe the system as one in which those big average spins are interacting with one another. So now you can think of each one of the big spins as interacting with its neighbors. So each big spin interacts with neighbors. But now the temperature keeps coming closer and closer to the critical point. And as it does so, the big spins start to get highly correlated with one another. And now there are even bigger spins in which many big spins form a droplet that points kind of in the same direction. And so then we do the whole thing again and replace that by a big, even bigger average spin. And after a while, after we've done this a few times and the temperature's gotten very close to the critical temperature, each time we take another coarse graining step, replacing lots of effective spins by an even bigger average spin, what we get looks like what we had in the previous step. We say that eventually, after we coarse grain a few times, after many coarse grainings, the coarse grain system looks just like the system before coarse graining. So in that case, we say the system scales. When we're very close to the critical temperature, the system has kind of a scale invariance or self-similarity. If you look at it in a more and more coarse-grained way, it still looks the same as it did originally. That's because it's got these fluctuations on all different scales. And when we average out the fluctuations on a small scale, we still have the fluctuations on a bigger scale. So it looks like the same as it did before, Okay? That's what I mean by scaling. But it looks the same only after some redefinitions of the parameters. So the new system, after you do the coarse graining, looks like the one before you did the coarse graining, but you have to tweak the temperature a little bit and tweak the order parameter a little bit so it'll look just the same. That's because the big average spin is the correlations between the spins on the droplets on bigger scales aren't quite as strong as the correlations on smaller scales. Or if I think about the response to an external field, I get a stronger response to the spins in little cells than I do from the average spin in a big cell, because some of those spins are pointing down, even though most of them are pointing up. Some of them are pointing down. So the average behavior of the big spin in response to an external field isn't quite as strong as for the little spin. So when we do this coarse graining, we describe average behavior in a big cell. These boxes I'm calling cells, just a box that contains a lot of spins. And it has a volume for the big cell, which is rescaled by some factor omega compared to the volume of a little cell. The big cell is bigger than the little cell. And the system, after I coarse grain, looks like the original one, except I have to change the strength of the external field. It's like I did last time. It's a little bit simpler to discuss this in terms of Gibbs free energy instead of Helmholtz free energy. And I wrote down this scaling hypothesis last time, which looks like this. Lambda is the external field. Epsilon is the dimensionless deviation from the critical temperature. So omega is like a volume factor. Since the Gibbs free energy is extensive, the Gibbs free energy in a big cell, which is omega times bigger, goes like omega times the Gibbs free energy in a small cell. So you can think of this as the Gibbs free energy in a small cell per unit volume times the total volume. And then there's a factor of omega because we've changed the volume of the cell. And then what this says is if we want the physics to look exactly the same, we have to make a little adjustment by some factor depending on the ratio of the volume of the big cell to the little cell to the external field and to the deviation from the critical temperature. So we have to adjust the external field for the reason I said, that the average spin in the big cell, it's a little bit softer than the average spin in the little cell because not all the cell's spins are pointing in the same direction. And we rescale the temperature because the big cells have weaker correlations than the little cells because they're bigger, and therefore, in effect, it looks like we're further away from the critical temperature after we do the rescaling. Okay? And that's where this type of scaling hypothesis comes from. Question?
Shouldn't it be closer because so you make it closer to the temperature, it gets more line, and you replace the chunk by one.
Yeah, so the idea is that as you're approaching the critical temperature, there's some characteristic scale over which things are strongly correlated. And it gets longer and longer as you approach the critical temperature.
Yeah, exactly. You're moving far away.
Sorry?
Oh, never mind.
Okay, so the correlation length is getting bigger and bigger when you get close to the critical temperature. But now suppose you do this coarse graining. that in terms of the new variables, now you're talking about the correlations between the cells. And the correlations between the cells have a shorter length than the original correlation length. In other words, in terms of the number of cells you have to travel before the correlations decay, that's smaller for the big cells than for the little cells. So you compensate for that by saying, well, I just moved a little further away from the critical point where the correlations aren't quite as strong. And that's why you rescale the temperature. Okay. So anyway, it's a long story how you can actually calculate the P's and Q's from some more sophisticated description of the fluctuations near the critical point than Landau theory, which we won't go into, but as you've seen in the homework, or will see by 5 p.m., just from this scaling hypothesis you can learn a lot, since you can predict the behavior of various critical exponents in terms of the P and the Q involving that describe how the Gibbs free energy scales. And because you can extract more predictions than the number of parameters P and Q, there are some relations among those quantities that you can extract. That's what you do in the homework. So the big lesson is that Landau theory doesn't work because of the large fluctuations. And that gives rise to this singular behavior. And to understand the singular behavior, which is encapsulated by the scaling hypothesis, you have to do a more difficult calculation that you won't learn how to do until you take more advanced courses. Mean field theory or Landau theory, since Landau theory is just kind of a general way of looking at mean field theory, should work if the fluctuations are not so big, if they're not so important. And the idea of mean field theory, if you think about our ferromagnetic model, for example, is that each spin is responding to the average behavior of all the other spins, or to the average of all the other spins. But that's not really what happens because of the fluctuations. Different spins are responding in different ways because their neighbors are fluctuating in different ways. But averaging over all the other spins is a more and more reasonable thing to do if you consider higher dimensional systems. For higher dimension, or higher spatial dimension, D, Landau should work better. The idea is just that each spin has more neighbors. In a one-dimensional system, it's only got 2. In a two-dimensional system, on a square lattice, it has 4. On a cubic lattice, it has 6, and so on. So each one of those neighbors is equally important in determining what a particular spin wants to do. If it has more neighbors, then it's a more sensible approximation to say that it's responding to the average of many other spins. And so what actually happens is kind of interesting. It's true that if you consider the dimension going to infinity, then Landau theory works. Because then there are lots and lots of neighbors. But you don't actually have to go to dimension equals infinity. There's some finite dimension is called the upper critical dimension. And when you're above that dimension, Landau theory predictions work. The exponents predicted by Landau theory, beta equals 1/2, gamma equals 1, and so on, are actually correct. So Landau predictions for beta, gamma, etc. work for spatial dimension greater than or equal to some so-called upper critical dimension. And that turns out to be 4. So Landau was extremely unlucky that the world is 3-dimensional. Yes?
What if real life has 4 dimensions?
Sorry?
What if real life is going to have more than 3 spatial?
Nothing. Sometimes an extra dimension can appear, for example, in the following way. This is actually it's a very good question. The answer isn't quite nothing. But for example, you could have a spin which has many components, so that the spin itself is like a little vector pointing in d-dimensional space, and I shouldn't call it d, an n-dimensional space, where n is very large, and so that sort of behaves like an extra spatial dimension. But the reality is that for most purposes, we live in 3 dimensions, and this is just bad news for Landau, right? That's why his predictions don't work. If we had lived in 4 or more dimensions, he would be even more famous. He's pretty famous as it is. How do we know? Well, it's a mathematical statement, right? So we can, it's a theorem, okay? Theorem. It's not a statement about comparing with experiment.
Is this the first theorem in?
Is this the first theorem in?
We had all exhibition.
I mean, almost everything's been a theorem. I mean, what do you guys think I'm doing here every day? I'm deriving things, right? This is what's different about this one. It's a theorem that I'm just telling you about and not proving, okay? Because it's interesting. Okay. Now, there's also a converse statement, which is when the dimension gets lower, then Landau theory is worse, or in other words, the fluctuations are bigger and have more important effects. And so it turns out that if you go to a low enough dimension, the fluctuations are so big that you can't have an ordered phase at all. So, for example, if you consider a magnetic model, so the converse is fluctuations become more important for lower dimension. In fact, so important when the dimension is low enough that spontaneous magnetization or in other words, order parameter not equal to 0 in the most probable configuration cannot occur for d less than or equal to some d lower, called the lower critical dimension. And d lower, well, actually here it depends on the symmetries of the system, but if we consider a uniaxial magnet, where the spin either points up or down, or an order parameter xi, which either takes a positive xi0 or negative xi0 value in the low temperature phase, the lower critical dimension is 1. We're talking about an axial magnet, but turns out to be 2 if we have a rotationally invariant magnet. So if you have a one-dimensional magnet, that just means you have a line of spins. So I'm saying that in that case there's actually no long-range order except at exactly 0 temperature. Cannot occur, I should say, for any temperature greater than 0. Because no matter how small the temperature is, there are always fluctuations which are big enough to wipe out long-range order. So a one-dimensional uniaxial magnet is disordered, not spontaneously magnetized, for any temperature greater than 0. And the idea is this. You got a bunch of spins in a line, that's what I mean by a one-dimensional magnet, and they interact with one another. The neighbors want to line up the same way. So at very low temperature you might have droplets of spins which all line up the same way, so they're happy. But then at some point there's a misalignment, and then another droplet occurs where there are many spins turned the other way, and then another droplet of up spins, and so on. Okay? So I'll call it a droplet of spins that all point the same way. What's the energy cost of a droplet, in which here the spins in the middle are pointing in the opposite direction of the spins on the left and the right? The energy cost just comes at the edge here, where we have spins which are misaligned with one another. If it's only the neighbors that interact and all the spins want to point in the same way, there's some energy cost. If we have a kink, so to speak, where the spins are misaligned, but it's just some constant energy cost. At any non-zero temperature, there's going to be some probability per unit length of having kinks. So when the system gets very long, there's going to be some number of kinks per unit length, which is non-zero, and that means the spins on average are going to be as likely to be up as down, right? Because the kink doesn't care how big the droplet of spins is that turns over. It only costs energy at the edge. So for tau greater than 0, kinks have a positive density per unit length. And that means no long-range order. In 2 dimensions, it's a different story, because in 2 dimensions, at low temperature, let's say most of the spins line up in the same direction, but then there's a droplet of spins that point the opposite way, surrounded by spins that all point up. So in that case, the energy cost of that droplet of flipped spins is proportional to the total length of its boundary. or the perimeter of the droplet. And so there will be, at low temperatures, some Boltzmann suppression of droplets, which is exponential of minus perimeter divided by tau. And so if the temperature is low, large droplets are going to be very rare. If the droplet gets bigger and bigger, its perimeter grows, its energy cost grows, and it becomes very disfavored to occur as a fluctuation. Okay? So that means the fluctuations are highly suppressed at low temperature for the two-dimensional magnet, but not in one dimension. So in 2 dimensions we can get, or 3, we can get a spontaneously magnetized low temperature phase. In 1 dimension we can't. So how do you actually compute this stuff? Well, there's some exactly solvable models where you can find P and Q. There's a kind of a general approach which works somewhat well that Wilson and Fisher originally suggested, which I'll tell you about only because there's sort of a moral, which is if you're a physicist and you're trying to solve a hard problem, you're kind of lost unless there's a small parameter. If there's a small parameter, then you can say, all right, I can start out with the approximation in which that parameter is 0. And then maybe I can try to systematically calculate the effects of that parameter deviating a little bit from 0. So now we know, or because I just told you, that Landau theory works in 4 dimensions. Okay? So for a small parameter, to try to get a handle on things, Wilson suggested the deviation of the spatial dimensionality from 4. So Fisher-Wilson, back in the early 70s, say, consider spatial dimensionality d. Well, I'm going to call it 4 minus epsilon, for which I apologize. It's not the same epsilon, but everybody calls it epsilon. Everybody calls that epsilon. What am I supposed to do? This doesn't mean the deviation of the temperature from critical temperature. It just means the deviation of spatial dimension from 4. So when epsilon is equal to 0, that's a case we can understand. We can use Landau theory. We're really interested in epsilon equals 1, right? That's d equals 3. But what they did is they worked out a way of systematically expanding quantities like P and Q in powers of epsilon in a power series expansion. So we can expand because we're expanding about something we understand. You can always do that. We understand Landau theory. Expand beta, gamma, all the things we'd like to compare with experiment as a power series in epsilon. And then, after carrying that out to some order, try setting epsilon equals 1, because we'd really like to know what happens in 3 dimensions. And there's no guarantee this will work. It depends on how rapidly convergent this expansion is. But in fact, it works pretty well. And you can understand this 0.32, for example, behavior of beta by carrying out this expansion to a few orders and setting epsilon equal to 1. Okay, so if you don't know what to do, look for a small parameter, and it might not be obvious how to find one. Yeah.
Does epsilon have to be integer in this model?
Well, no. So of course you probably are wondering what it means to do statistical physics in 3.99 dimensions. It's a good question. But so what they really do is they write down a bunch of integrals, right? And so they have a formula that depends on dimension, and really those formulas only make sense when the dimension is an integer. So then you have to tell a story which is, in the end, I think, not completely convincing about how, well, it actually makes sense for every integer dimension, and if you think of it as some analytic function, maybe you can argue, if you know something else about the properties of that function, that it has a unique analytic continuation away from the integers. So we can define a function of d that really depends continuously on d and is defined off the integer values. Really, they just looked at some formal expression which had d's in it and said, suppose those d's are real numbers instead of integers, without any a priori justification.
When they do the math, they actually treat it as a real number. And then when they
Well, actually, you can treat it as a complex number because you're doing a power series, so you're treating it as an analytic function of d, which has singularities in the complex d plane and all that fun stuff. But it works. It doesn't work great, but it works okay. You can do a lot better than Landau theory, and that's something else that if you continue in physics, you'll learn about, because this subject of critical phenomena and scaling is really central in modern physics, in classical quantum statistical physics, and in particle physics too. So just one last remark. So the great idea about Landau theory was it was universal, right? It didn't depend on the microscopic details. So the scaling theory also has that property. So these scaling functions apply to a big class of microscopic models which all scale the same way. But not everything scales the same way. There are so-called universality classes. To a certain extent, the microscopic physics doesn't matter. You can consider lots of models which have the same universal properties. If you're in a certain universality class, then you have the same value of P and Q in this scaling ansatz, and therefore all the predictions that follow from the scaling hypothesis. But not everything's in the same class. A class depends on the symmetry of the model. So, for example, a uniaxial magnet, which has the order parameter goes to minus order parameter symmetry, and a rotationally invariant magnet, which has a symmetry in which the order parameter is actually a vector, and it gets rotated by some matrix, like the rotation matrix, and that leaves the dynamics of the system unchanged, because no matter how you rotate the magnet, it looks like the same magnet. These have different symmetries, and they're in different universality classes. We could already infer that from what I said about the lower critical dimension, which is different in the case with psi goes to minus psi symmetry and continuous rotational symmetry. But there's still universality in the sense that you can consider any magnet model you like with some kind of local interaction among the spins. As long as it's rotationally invariant, it'll be in the same universality class, and the predictions will apply to it. Okay. So that's it for critical phenomena. So we got a half hour today, and next week we have to decide what to do. I'm going to do a little kinetic theory. There's a lot of other stuff in the book. A lot of it's fun. Much of it is applications of the principles that we've been learning up till now. But I think from a fundamental point of view, kinetic theory is probably the most important thing in the rest of the book. And in particular, I want to say something, though I won't get to it today, about a topic that we haven't discussed very much, and that, except in the context of critical phenomena, that is the consequences of deviation from ideal behavior in gases and other fluids, the effects of molecular collisions, in other words, on the behavior of a substance. Well, this is chapter 14 in Cattell and Cromer. And basically what kinetic theory means is, well, it means understanding macroscopic behavior from the point of view of microscopic dynamics, which in a sense is what we've been doing all along. And so what I'll do is first, I'm sorry about this, but I'll talk about the classical ideal gas a little bit more. But then I want to say something about diffusion, which is a consequence of non-ideal behavior. That is, from the fact that particles collide. They're not really non-interacting. And the reason is that diffusion is really a ubiquitous phenomenon in all kinds of physics settings. It's the key to understanding heat conduction, which is really diffusion of energy, electrical conduction, which is diffusion of charge, viscosity in fluids is diffusion of momentum, mixing of materials, like if we allow two different species of gas to mix with one another, that's a diffusive process. So to understand all these things, we should know something about diffusion, and that arises from the fact that gases aren't really ideal. The molecules collide. But first, let me, like I said, consider a classical ideal behavior, again, from a somewhat different point of view than before. I want to revisit the concept of classical equipartition. So, in general, if we consider computing the internal energy of a system in the Boltzmann ensemble, we say, okay, the mean value of the energy is the sum over all states of energy weighted by Boltzmann factor, and then we divide by the partition function to normalize it. So suppose, for example, I consider an ideal gas. I have n particles in 3 dimensions, not 4, 3. But I know how to do the calculation for 4 dimensions also. But yeah.
A question about the ideal gas. So in ideal gas, we assume the volume of particle is small compared to the total volume.
Well, that's part of it, right?
And also the particles are non-interact.
Right.
So here it's diffusion is non-ideal because we consider it a particle collision.
Yeah.
But without particle collision, how do we even make sense of pressure?
Well, I want to make a distinction between the collisions of the particles with the walls of the container and the collisions of the particles with one another. So in particular, I guess we'll talk about this next Tuesday. That's the ideal gas model, right. And so the important property of the non-ideal gas is that if I follow the trajectory of a single particle in a large chamber, it has a mean free path. It changes the direction of its velocity on some characteristic time scale. It does that because of the collisions with the other particles. So if you put a number on the back of a particular molecule and followed what he was doing, he would make some kind of random walk because of collisions with other particles. And that's the aspect of non-ideal behavior that we'll want to discuss to understand these phenomena. Okay? So in particular, if I add some energy locally in the system, so some of the gas is a little bit warmer, how long does it take that heat to spread out? Well, it's going to be delayed because of the collisions with other molecules. So it's going to spread out gradually, and that's the origin of heat conductivity. That the fast molecules have to make a kind of random walk in order to travel a long way. Okay. Oh boy, that was my closest call yet. Like you said, this is a good opportunity to get do another row. Okay. I'm just stalling, I guess. Who wants to? I don't think so, because I'm pretty damn likely to trip over it now. Or even before. Okay. So if I consider an ideal gas, I can classically, what is it? It's just a bunch of particles, and each one has a position and a velocity. So in the classical case, I can completely characterize it by the position in three-dimensional space of each of n particles. That's not enough by itself. I also need to know their velocities or momentum. But if I know the position and the momentum of each one of n particles, I know everything classically, right? Now, suppose we're talking about one particle. As we've discussed many times, if we have a particle in a box, we can sum over all of its orbitals. When we sum over orbitals, I can replace that by a factor of volume divided by 2 pi h bar cubed if it's a particle in 3 dimensions, and then I have an integral over momentum. I guess sometimes I've written it as an integral over the wave number, but here I've written h bar times the wave number to get momentum, and then I divided by h bar in the prefactor. So you can think of this volume as arising from integrating over the position of the particle. So it's really summing over all of the states for a single particle is doing a three-dimensional integral over its position and its momentum and dividing by 2 pi h bar cubed for a particle in 3 dimensions. Since h bar is really h over 2 pi, if you like, we could call that h. And that's a nice formula because it's kind of easy to remember. It means that we can think of each quantum state, which is what we're counting here, as occupying a volume in this 6-dimensional phase space, which is Planck's constant h cubed. Okay? But if we want to do classical statistical mechanics, Maxwell and Boltzmann and those guys, they did all kinds of classical statistical mechanics. They didn't know anything about h bar. In fact, all we're going to need to know to understand what those guys did sorry, they were all guys, is that summing over states is the same thing as integrating over the 6-dimensional phase space for each particle times some constant. And the constant's going to drop out of the things that we compute. So counting states to a classical physicist means integrating over position and momentum for each particle up to some normalization constant, and it doesn't really matter how I choose it. So suppose, in particular, I'm talking about an ideal gas in which the energy is just the kinetic energy. There are no interactions, so no potential energy. And if the particles all have mass m, the kinetic energy is the sum. Actually, it doesn't, for what I'm going to say, it doesn't matter whether they all have different masses, but is the sum of momentum of the first particle squared divided by 2m up to the nth particle squared divided by 2m. And so when I compute the expectation value of the energy, well, I actually get 3n terms. Each one of these you can think of as 3 terms, the x squared, y squared, and z squared components of momentum. So I get 3n terms, and they all look the same because when well, maybe I shouldn't. Maybe I'm doing too many things at once. This is the integral now over phase space for the first particle, second particle, etc., up to the nth particle in the numerator, and then I have e to the minus e over tau. And the denominator, I have almost the same thing except no factor of e. So that's what I've got. But this is just a sum of 3n terms, these 3n terms. So suppose I pick any one of them, like the x component of the momentum of the first particle squared. Then all the integrals divide out between numerator and denominator, right? Because I don't have... the e just multiplies e to the minus x component of p1 squared over 2m, and the integral over everything else is the same in the numerator and the denominator. And I have altogether 3n such terms. So we have 3n, and then times an integral over one particular momentum of 1 over 2m p squared, e to the minus p squared over 2m times tau, divided by an integral dp, e to the minus p squared over 2m tau. So just by multiplying and dividing by tau, right, because I got a p in the numerator and the denominator. After rescaling the integration variable, shouldn't be 3n equals 3n times, and this is equal to u, because I have 3n such terms, and so that just becomes tau times this dimensionless integral. So this is 3n tau, and then I have the integral of dx, x squared e to the minus x squared, where now x squared is p squared over 2n tau, divided by integral dx, e to the minus x squared. And that's just a dimensionless number, which is 1/2. The momentum, and hence x, is being integrated from minus infinity to infinity in numerator and denominator. So that's just 3/2 n tau. So as you already knew, the average energy per particle in the classical ideal gas is 3/2 tau. But now let's look at this from a somewhat more general point of view. We wrote an energy function which was a sum of squares. Okay? It was just some quadratic function. It could have been any quadratic function. And we would have had a similar derivation. Namely, what we found is that for each one of these terms, the contribution to the internal energy was 1/2 of the temperature. Right? Because every quadratic quantity appearing in the energy gave a contribution which looked exactly like this, just a factor of tau times this ratio of dimensionless integrals, which is 1/2. So if the energy is equal to sum of squares of variables, phase-space variables, that means that U is equal to 1/2 tau for each term. Suppose we had many harmonic oscillators instead of many free particles, for example. Then I would write the energy as the sum over a label for the oscillator, 1/2 the mass of oscillator I, momentum squared plus 1/2 mass times frequency squared xi squared. Well, each one of these appears quadratically, each momentum and each position. And so I could do exactly the same analysis that I just did. Look at the terms one at a time, divide out all the integrals in numerator and denominator that are the same, and I'd be left with a 1/2 tau for each variable that appears quadratically. So I get 1/2 tau for each pi and 1/2 tau for each xi, contributing to U. So in the case of n harmonic oscillators, if the sum goes from 1 to n, well, maybe that's confusing because I want to use n to mean something else in a minute. So let me just put it this way. The internal energy classically, if the energy is a sum of squares, is equal to 1/2 tau times a number of quadratic degrees of freedom. So suppose, for example, we have an elastic solid. So we have n atoms in 3 dimensions. And that just behaves like 3 n harmonic oscillators, right? Describing the vibrations about equilibrium of the position of each one of n particles in 3 dimensions. So we have 3n xi's. Well, I don't know. 3 because we're in 3 dimensions and n atoms Oh, I'll just say 3n times 1/2 tau from positions plus 3n times 1/2 tau for momenta. So altogether, 3n tau. Correspondingly, the heat capacity is 3n. That's just what we called before, when we encountered it as a limit of Debye theory, the law of Dulong and Petit. It's just this classical equal partition principle again. The principle that every quadratic degree of freedom contributes 1/2 tau to the total energy. Now we know quantumly that this applies only in a certain high temperature limit, the so-called classical limit. So this classical equal partition is a temperature going to infinity limit of quantum theory. And so in the case of a harmonic oscillator in particular, we know the expectation value of the energy of a single harmonic oscillator, as we've discussed a number of times by now, is the level spacing h bar omega times e to the h bar omega over tau minus 1, which becomes just tau when tau goes to infinity. Well, that's two quadratic degrees of freedom, each contributing 1/2 tau, the x and the p. And it becomes something small at low temperature, h bar omega times e to the minus h bar omega over tau as tau goes to 0. So we say that the degree of freedom freezes out and gives a much suppressed contribution to the total energy in thermal equilibrium when the temperature is small compared to h bar omega, where omega is the frequency of the oscillator. But the classical equal partition principle kicks in at high temperature, high compared to that oscillator level spacing. So just one more quick remark, which also recalls something I said earlier. So I can summarize this by saying when we speak of equal partition, one-half tau contributes to U for each accessible quadratic degree of freedom. Where accessible means not frozen out. That's sufficiently high temperature compared to the characteristic energy scale that it behaves like a classical variable. So if I consider a gas, a molecular gas, like a gas of dipolar molecules, in addition to the center of mass motion of each molecule, we can also consider vibrations, which has some characteristic frequency omega, and the rotations of the molecule around either one of two axes. It can either rotate out of the plane of the board or in the plane of the board. And in the case of the vibrational modes, of course, the spacing is just h bar omega, where omega is the vibrational frequency of the molecule along its axis. And in the case of rotation, the energy is 1 over twice the moment of inertia of the molecule about the midpoint of the axis times angular momentum squared about either one of the two axes. Call that L1 squared and L2 squared. These are also quadratic degrees of freedom. So in this case, since it's an oscillator, when it's accessible, that contributes another tau. There's an x and a p in the harmonic oscillator when that degree of freedom is not frozen out. And this is also another tau, since there's a angular momentum squared about each one of the two axes, two more quadratic degrees of freedom. So for the internal energy, from the center of mass motion, we have 3/2. I guess I'll write it this way. We have n tau times 3/2. That's because there are 3 quadratic degrees of freedom, the 3 components of momentum. And at high enough temperature, plus another 1 for the 2 rotational degrees of freedom, plus another 1 for the vibrational degree of freedom. These freeze out at different temperatures. In fact, the rotational modes are present at lower temperature than the vibrational modes. The vibrational modes freeze out at a higher temperature for typical molecules. So what we'll actually see in the if we look at the heat capacity as a function of temperature divided by n. Actually, at very low temperature, we're in the quantum regime where the heat capacity goes to 0. But then when we enter the classical regime, it'll be 3/2 per particle. But that's because the vibrational and rotational degrees of freedom are frozen out. And then it will jump up to 5/2 because of vibrations at a sufficiently high temperature. Rotations come in first typically because of rotations. And at a still higher temperature where vibrations are not frozen out, it goes up to 7/2. But anyway, the principle is oh boy, that was a close one. 1/2 tau for each quadratic degree of freedom, which is accessible, meaning at sufficiently high temperature, with some characteristic energy spacing, in this case determined by h bar squared, the typical value of angular momentum and the moment of inertia, and in this case determined by the vibrational circular frequency. At sufficiently high temperature, the degree of freedom becomes accessible and then contributes 1/2 tau to the total energy per particle. Okay.